This is Module 14, Lesson 3. This is the last lesson in this module. Today we're going to be looking at heat that comes from changes in state. Remember that changes of state are phase changes like melting, freezing, vaporizing, and condensation. Those are the four that we're going to look at. They're the most common. So as we begin, let's look at this phase change diagram here. This is what's known as a heating curve, and it's a heating curve because, as you can see, as time goes by to the right, temperature is increasing. They actually have cooling curves, which, as you might imagine, are the reverse of this because as time goes by, the temperature is still here on this axis. The temperature goes down as time goes by. So either one of them, what you need to recognize is that in this lowest portion, you have a solid. The middle is a liquid, and the upper section is a gas. All three of these can change temperature. So when we've been looking at the Q is equal to MC delta T problems, we have been working these whenever the temperature is changing, hence this part of it. If you have a change in temperature, then you either have a solid, a liquid, or a gas. If you are in the middle of a phase change, as you can see according to this particular graph right here, if you're in the middle of a phase change, then your temperature doesn't change. Right here is melting and freezing, and then up here you have vaporization and condensation. So as you can see from this, at whatever temperature your substance is going to go through the phase change, the temperature doesn't change at all. If this is water, then right here you have 0 degrees Celsius, and right here at the end of it you still have 0 degrees Celsius. So water can freeze or it can melt at 0. That sounds kind of crazy, so how does it work? Well, the basic idea is if energy is being put into the substance, if it's being absorbed, then you're in the process of moving this direction. If the energy is being removed, then you're in the process of moving the other direction. So you would just have to look at whether energy is being absorbed or released. If you have a solid and you have your molecules that are all together, remember that they're very attracted to each other. And so when you're adding energy, you're having to overcome those attractions and break them. That's why energy needs to go in to melt it. But then in a liquid, you have to take the energy out of it to get everything back into this nice orderly formation. Same thing is going on up here at vaporization and condensation. If you enter this, if it was water, I made the screen pop up. If you enter this and it's water, then it's going to go into the phase change at 100 degrees Celsius, and it's going to come out of the phase change still at 100 degrees Celsius. So if you're in the process of vaporizing it, you're in the process of converting it over to a gas. Now, by the time it becomes a gas, the temperature can continue to increase. If you want to try this for yourself, you could do a little home experiment. You could take some ice and sit it out on your counter, stick a thermometer in it, and watch and see that as long as there's still ice in that container, it's going to stay at whatever the freezing point is. You may not get exactly 0 degrees. You may get 1 degree Celsius or 2 degrees Celsius. It may not be right at it. You could do the same thing with boiling, but be careful if you do it. You could boil water on the stove and see that, it will not go above the boiling point. Even if you keep the stove on and heat just keeps going into it, it will not go above the boiling point as long as you are in the process of converting more of it to steam. So what we need to work with today is we need to work with the math of these phase changes. So the idea behind it is this. Let me erase some of this just so that it's not so much in our way. But the main idea is based on the equation that we used before, which you can see right here. This is our equation from before. We can't use this in a phase change because of this change in temperature thing. If it starts out at 100 and ends at 100, 100 minus 100 equals 0. So if we put that in there, I don't care what the mass is, and I don't care what the specific heat is, it's going to be times 0, which means there's no heat. And we know that not to be true. So what we're going to look at today is a series of equations. They're on your reference table. I'll show them to you in just a minute. But they look like this. They both have MH. They have little m, which you should recognize as mass. And this H stands for heat, basically. And so we have HF and HV. So let's look at those for just a little bit and how we do this. What you can see with these is that they don't take into account temperature. So first of all, we need some vocab in order to do this. So you can take just a moment to copy these down, and when you're ready, continue with the video. So as you can see, this delta H fusion, it's represented on your reference table just as H with a little f. If you look at your reference table, you will not see delta H of solidification. There is no HS or H solid. Here's your reference table. Here's what you see. You see right here the heat of fusion of water right here on your reference table. And you have one number, and it says HF and water. So this is the heat of fusion of water. What you need to understand is this means this is the heat that is necessary to melt however many grams of water. So in other words, if I have, it's joules per gram, so it's 334 joules for every 1 gram of water. So if you have the amount of water, so if we have Q is equal to MH, if we have the mass of water in grams and we have this H, we can just multiply them. Now, since there isn't a delta HS, here's what you need to recognize. You need to recognize that they're opposites of each other. So, in other words, on your reference table, if the delta HF of water is 334, what that means is that the HS of water is negative 334 joules per gram. It's just the polar opposite of this. All right. Here's your other two. You have molar heat of vaporization and molar heat of condensation. So again, take a moment, get these down, and then come back when you're ready. This is a capital H, by the way. Okay, so as you can probably imagine, this is for vaporizing and this is for condensing. On the fusion and solidification, those don't make quite as much sense, but it's the words that are used. This is going to work out the same way on the reference table. You're going to be given the H of vaporization, and then it's up to you to know that the H of condensation is the negative of the H of vaporization. So let's look at that and let's see it. So here is the other one. So what we're going to see this time is the, oops, I thought I switched colors, but maybe not. I don't think that's a little on the purple side. You have the heat of vaporization of water is right here. It's a lot greater than the heat of fusion of water. It takes a lot more energy to increase the temperature of water in order to vaporize it than it does to melt it. So that means that the H of condensation is negative 2,260, and that's joules per gram. So what do we do with these now? First of all, don't get them confused with specific heat. This is entirely different. Secondly, there's a couple more things that you might see. You have molar heat of solution as well. So you could take a moment to put this down. Sometimes as things dissolve, they will give off heat. So if you have an H of solution that is positive, excuse me, what that means is that it absorbs heat. And if you have one that's negative, that means that it releases it. The first one is endothermic and the second one is exothermic. Another thing that you may see is an H of combustion. And obviously what that means is the heat that's given off as something burns, because combustion is about burning. So these are going to be negative because burning something releases a lot of heat. So you could see these other ones. If you're given those, they're going to work the same way that we're getting ready to do our sample problems. So you're going to need your practice sheet because these sample problems are on there. And here's your very first one. Okay, so it says how much heat is required to melt this many grams of water at 0 degrees Celsius. How do I know that this isn't the Q is equal to MC delta T problem from the previous lesson? Well, first of all, it says the word melt. That registers in my mind as a phase change. And secondly, there's no temperature change. So if I try to plug this into this equation, it is not going to work purely because of the delta T. So this is a big no. We're going to have to plug this into Q is equal to MHF. Well, and honestly, when I work these in face-to-face classes, I just leave the F and the V off of them. It doesn't matter. You just need to figure out which H goes there. So since this is melting, on our reference table, we're going to use the heat of fusion, and it is melting, so we're going to use the 334 joules per gram. So the mass is 789 grams from above, and that is times 334 joules per gram. Grams cancels, and at this rate, we are left with an answer that will be quite large. On your quizzes and things, most of the time I'm going to ask you to do your answers in kilojoules. So if we have 263,526, it'll be that many joules. If you're going to do this in kilojoules, then you need to move your decimal space 3 spaces to the left. So that would make it 263.526 kilojoules. And since we can only have 3 sig figs, we're going to cut it off to 264 kilojoules. When you get large numbers, it's nice to give it in kilojoules instead of joules. All right, that's all we have to do with this. Here's another example. How much heat is released when this many grams of water freezes and then at 0 degrees Celsius? So just like last time, I see the word freeze. That's a phase change, and I don't have a temperature change over here. So we're working another Q is equal to MH problem. Our mass is 432 grams. Our H, well, this is freezing. So I'm going to have to look at this and know that I'm going to use the negative version of the heat of fusion of water. Fusion is for melting. So for freezing, we're going to make it negative 334. And so negative 334 joules, that's per gram. Grams cancels. Now, some of you may be thinking, like, does it really matter if I use the whole negative thing or not? Well, yes, it does. You know enough at this point to know that negative Q values are representative of exothermic things, and positive Q values are representative of endothermic things. So, yes, it does matter. Now, if I ask you to give your answer in kilojoules, you have to move your decimal over. We get to keep 3 sig figs, so the first 3 digits stay. So that's negative 144 kilojoules. Now, there's another answer that I find to be completely acceptable, and that's if you want to put 144 kilojoules released, or you could say emitted, given off, some word that's a synonym of released. This is, you don't want to say both. You don't want to say negative 144 kilojoules released, because that's kind of a double negative. So you can either use the sign or you can use a word. And I will have the quizzes set so that you could do it either way. If you do not include the negative, then your quiz answer will be wrong. You can either include the negative or you can include the word released. All right, one last example. How many joules of heat are given off when 5.9 grams, I don't know what happened to my pen there, 5.9 grams of water are condensed? So I see condenses, which means to me that, I'm doing another phase change thing. Q is equal to MH. Well, the M is 5.9 grams. The H is, let's see, we're doing condensing. So you're going to have to know that it's the opposite of this one, which means that we're going to do negative 2,260. So this is negative 2,260 joules per gram. And we're going to come up with another negative answer, which is fine. We have negative 13,334. Now, it does say how many joules. However, I'm practicing the kilojoule thing since I'm asking you to do that on the checkpoints and the test, just because it's smaller numbers to deal with. So if you convert this to kilojoules, you have to move it over 3 spaces. I can have 2 sig figs, which is 13, so it's negative 13 kilojoules or 13 kilojoules released. Okay, either of those answers is perfectly acceptable. So that's all there is to this. So what I have is that it's practice time. You have a small practice sheet that includes 7 problems. One of them that made it on there is a little bit different. You have a delta H of solution problem, but it's the same idea. And then after this, you actually have some mixed review problems where I do mix it all up and try to include all the things that we've learned in lesson 1, 2, and 3 to make sure that you can differentiate before you get to the test as to which equation you're using. If you're doing Q is equal to MC delta T, are you doing Q is equal to negative Q, or are you doing this Q is equal to MH thing? If you need help, then be sure to find me in office hours or send me a message and we'll see what we could do.